Okay, it looks like everybody's here, and I'm sure the anticipation of another one of my lectures is just almost more than your hearts can withstand. But anyway, today we're going to sort of start the second half of this class, which is on optical oceanography, which you've been doing, and then getting into remote sensing, which you're going to be doing a lot more of, especially next week when Jeremy Wardell shows up. So this lecture is just going to be defining a lot of terms, showing you what this so-called atmospheric correction problem is all about. And Jeremy asked me to put that into this lecture so he would have more time to tell you how NASA solves the atmospheric correction problem. So what we're going to do today is just talk about basic terminology that's used in ocean color remote sensing. And then, a lot of you probably know that, but probably some of you don't. I'll talk a little bit about forward and inverse models. And remote sensing is an inverse modeling problem. And we've already talked a bit about AOPs for remote sensing, like the remote sensing reflectance and the irradiance reflectance. So I'll just kind of briefly run through that. And then, let's see, you guys, it's kind of backward. You've already done things like the Carter method and the Lee method out on the dock, and so now you'll see the theory, but I think you probably know that anyway. So we'll go through that, I think, fairly fast, and then I'll show you some examples of what this atmospheric correction problem is all about. So first of all, when people talk about their remote sensing imagery, they have all of these ways of kind of classifying what kind of image it is. One of which is the spatial resolution, which is the ground size of a pixel that's seen from the aircraft or a satellite. Now, from satellites like CWIFs, MODIS, VIIRS, they tend to see about a kilometer-sized pixel on the ocean. If you're flying an airborne system at 3,000 meters, for example, they may see 1 square meter per pixel. And there are actually satellites that see like a 30 centimeter square pixel on the ground. Now, the signal to noise ratio is crap. There's calibration's terrible and all of that, but you can actually see some guy walking down the street by the size of the hat I'm wearing. So anyway, that's one way to classify the quality or the level of the imagery. Another one is the spectral resolution, which is simply the number and width of the different wavelength bands that this sensor is seeing. There's the radiometric resolution, which is simply how many different magnitudes or intensities of radiation the sensor's able to distinguish. So, for example, you'll see people say, well, this is a really old sensor, it's only 8-bit resolution. Well, that means that it's taking the signal that goes from dark, no light at all, up to the brightest light it can measure, and it's dividing that into 2 to the 8th or 256 levels of when it digitizes the signal. So a dark signal would be a value of 0. The brightest signal it could measure at that wavelength would be a value of 255. So generally starts counting with 0. And then a really, really sophisticated sensor might go up to a 14-bit sensor, meaning it can go to 2 to the 14th or 16,000 levels or shades of color in each band. And of course, even though you have 16,000 levels, you may not be able to use them all because you've got all these issues of sensor noise and so forth that come in there as well. Then there's the temporal resolution, which is simply how often do you acquire imagery. With a satellite, maybe the satellite goes over a given area every 3 days. It might be every 2 weeks. With an airborne system, you only get an image if the airplane goes out and flies. So maybe right after a hurricane, the airplane's flying all day long and you get an image every 2 hours, but then that only lasts for a week. And I was recently on a big proposal review panel, and everybody was talking about how my sensor's going to do 4H remote sensing, 4H this and 4H that, and I have no idea what they're talking about. Well, that's the latest buzzword for 4H is high spatial, high spectral, high signal to noise, and high temporal. Well, of course, that's what everybody wants to have, but so, you know, yeah, next year there will be some other, it'll be like 5H or something because they've cooked up something else. So anyway, that was the first new acronym I had to learn to read these proposals and stuff. So then on the spectral resolution, well, when you talk about a monochromatic sensor, that means it's sensing or using one very small wavelength band, like the 532 nanometer band of this laser. Whereas panchromatic means we're also just looking at one wavelength band, but it's a very broad band. So a black and white photo is a panchromatic image. So typically, you know, somewhere covering the visible, or maybe, you know, centered at 500 plus or minus 100 nanometers, something like that, you would call panchromatic. Then multispectral means you typically have 5 or 10 wavelength bands. They're typically 10 or maybe as much as 20 nanometers wide. So your sensors like CWIFs and MODIS and VIIRs and so forth are multispectral imagers. And then hyperspectral, you have 30 or more bands with at most 10 nanometer resolution. Typically you may have like 100 bands and maybe 4 or 5 nanometer resolution. The catch is for a multispectral sensor, you've got these bands here, and there's a band width which can, you know, pointed out, you take the half the height, and whatever that width is the band width, and in the middle of that is the band center. So there's a band width, and then there's a sampling interval, which is how often do these bands occur. Well, that's the multispectral thing. Hyperspectral, often these bands will overlap. So you say, well, I've got like 4 nanometer resolution on this airborne system, but this is every 4 nanometers, but the bandwidths might be 6 wide, so there's kind of some overlap there and things blur together. So that's just the terminology for spectral resolution. And then NASA, and I guess this is now kind of the global standard, they have these different processing levels. So you read the proposal and it'll say, we're going to take the level 1B data and we're going to do whatever. They'll never define what that is. You're just supposed to know it. Well, the level 0 data is what the sensor on the satellite is actually measuring. So that's something like volts or digital counts, whatever that instrument is designed to measure. And then when you acquire the level 0 data, NASA then sticks onto that information that says, where was this sensor exactly when this image was acquired, what direction was it pointing, and so forth. And then there's also calibration files that are needed to turn something like volts or digital counts into something we work with like a radiance. So they take the level 0, this raw data, full resolution of whatever the instrument sees, and then they append these georeferencing parameters so you know where it was acquired, and they stick on the file of calibration coefficients, and that's then called level 1A. And then the level 1B is you actually take this appended information and use it to turn your digital counts or whatever it is into something like radiance units, which is what we really want to work with here. And so then once you've done that, you can start doing science. So science begins with level 1B data. You haven't done atmospheric correction or anything yet, but if you want, you can go to NASA, get the level 1B data for the Gulf of Maine, and then do your own atmospheric corrections, you know, apply your own algorithms, whatever you want to do. And once you've got this data here, you no longer have these calibration coefficients and so forth attached to your imagery, so you can't go backwards, but that's okay. And you don't want to look at that stuff anyway. It's really ugly engineering. Okay, so then what you do, or what NASA does generally, is they take the level 1B image and they do this whole atmospheric correction process that Jeremy Wardell will talk about next week. And so that takes the radiance at the top of the atmosphere here and turns it into a normalized radiance or normalized reflectance at sea level. And that's what you can then stick into like a chlorophyll retrieval algorithm and come up with what you're probably really interested in, which is what's going on in the ocean. So this is the big step here, is getting from level 1B to level 2. And then after they do that atmospheric correction, NASA also takes their suite of algorithms for retrieving like 24 different things from chlorophyll to KD at 490 and A and BB and all these other things. And they process all of that, and then they put out at level 2 derived geophysical variables. That is, it's the normalized water leaving reflectance, the chlorophyll concentration, CDOM, maybe bottom depth if it's an airborne system, and so forth. And those are all at the same spatial resolution as the level 1 data up here. And so a lot of people, if you're interested in looking at chlorophyll in the Gulf of Maine, you just want to download the level 2 data and do your thing with that. Okay, then level 3 data is they take this and they map it onto a uniform space-time grid, because remember, this image here may be looking off at some angle and it's sort of spatially distorted and all that. So then you want to put that onto a nice latitude-longitude grid. If there's missing points due to bad pixels or small clouds or whatever, then they may interpolate, fill in those regions. They may take multiple images and stick them together and then make one big image of the Gulf of Maine, for example. Ken? Or you're just scratching fleas? Okay. And then, so that's also, you know, widely used for doing science. And then the level 4 is you take the actual retrieved outputs and you use that in some other model, like an ecosystem model. So you take the, you know, let's say the CDOM concentrations and the A's and B's and all of that, and the inputs of whatever, and you run an ecosystem model and predict what the ocean is doing, and then you put out a map of that. And so that's then level 4 data. And I don't see too many people in my community working with this. They all live up here somewhere. But anyway, you then get maps or images of variables that were not measured by the instruments themselves, but were derived from what the satellites did measure. So Jeremy next week will spend a lecture or two getting from here down to here. Okay, the whole business of modeling, just once again, some more terms here. First of all, a model is just some representation of the real world, and in the model you try to retain the essential features of what's going on in nature, but not have in the model the less important details. And so the model could be a physical model. I mean, we could go make a model of the Damariscotta River estuary, and it might be the size of this room, and there's a piston down at the south end that pushes water back and forth to simulate the tides and so forth. Or it could be a numerical model where you model the same thing, but just using the equations of hydrodynamics to simulate the water going back and forth in the estuary. Okay, so anyway, models can be either predictive or diagnostic. So a predictive model means that you take whatever inputs you have. In the case of hydrolite, for example, you're going to put in IOPs and where the sun is in the sky and those sorts of things. And you're then going to predict whatever it is you're interested in. So the radiances or the irradiances or reflectances or whatever. So that's a predictive model. A diagnostic model is basically curve fitting to the data you've got. So you have measured whatever it is, you've analyzed it, you've transformed it, smoothed it, whatever, or maybe you simply fit a curve through it. And now you've got a model that will, given whatever it was, will predict whatever else I have. But really all you've done is fit a curve through data and use that. So it's a diagnostic model. It tells you, here's what was going on in my data. Then there are direct or forward models versus inverse models. So in radiative transfer theory, a forward model will take the IOPs as inputs, solve the radiative transfer equation, and predict the light field. The inverse will be to take the light field and go backwards and try to back out the IOPs. So that's just another way to classify models. So hydrolight is a forward model, Monte Carlo models are forward models, remote sensing is an inverse model. We're going to take a measure of the light and deduce something about the oceans. Then you'll see people say, well, I have this analytical model, I have an exact numerical model. What's that mean? So an analytical model simply means you can work it out with pencil and paper. So I mentioned the other day this single scattering approximation to the radiative transfer equation, although we haven't looked at that, but it's basically a pencil and paper approximate solution of the radiative transfer equation where you assume that there's only one scattering event. And then exact numerical models, so hydrolight or Monte Carlo, they're going to do a lot of number crunching with a lot of fancy math and give you an accurate solution of the radiative transfer equation. And exact, it turns out, in radiative transfer theory, it doesn't mean it gives the correct answer necessarily. It means you haven't built in approximations like assuming there's just one scattering event. So exact means I'm taking the full equation and I'm going to solve that. And then if you put in bad input, you still get bad output. And then there are deterministic versus probabilistic models. Deterministic means there's no statistical noise, so hydrolight's an example of that. Probabilistic means that there's statistical noise in the solution because you're using some technique like Monte Carlo simulation, which is inherently a probabilistic thing, and you'll see how both of those work in the second half of the class. But when you read a paper, people will talk about, I use this kind of model, whatever, this is what they're talking about. So basically, for a forward problem in radiative transfer theory, you really start out with very fundamental information like particle size distribution, index of refraction, maybe the absorption properties of dissolved substances. But when you look at the radiative transfer equation, it doesn't have in there particle size distribution. It has in there absorption and scattering. So you take this very fundamental information, you parameterize it in the IOPs so that, yeah, you have a scattering coefficient and a volume scattering function, and that's what's in the radiative transfer equation. And those things, the volume scattering function, does depend on size distribution, index refraction, etc. But you don't have to deal with that level of detail. And then you have boundary conditions on, our case, it'll be the radiance from the sky onto the sea surface and maybe the bottom reflectance. And so this IOPs and the boundary conditions go into the radiative transfer equation, which you can think of as a very complicated math model that relates these things to the radiance distribution. So this is a solved problem. If you give me IOPs and boundary conditions, I can use one radiative transfer model or another, and I can compute this with just as much accuracy as I want. It's just a matter of computer time. So, and you can see the radiative transfer equation. It's a predictive forward model with these as input parameters. Then remote sensing is an inverse problem. And there the problem, and also I should point out here, if you give me a set of IOPs and a set of boundary conditions, there's only one radiance distribution you're going to get out. So it has a unique solution. With remote sensing, that's an inverse problem. We're going backwards from the light field to the IOPs or boundary conditions. And inverse problems usually do not have a unique solution. So there can be, for example, if I give you RRS at one wavelength, well, to first order, the remote sensing reflectance, RRS, is proportional to BB over A. So if I give you a BB value, and let's say BB is 0.007 per meter and A was maybe 0.1 per meter, and I run those through Hydrolite, I'm going to get a particular value of remote sensing reflectance. So maybe that gives me 0.004 per steradian for RRS. Okay, unique solution. On the other hand, if you give me this value, well, I could have this solution, or I could have 0.014 and 0.02. The ratio's the same, and I get the same RRS. So I don't know which one of these was correct or any other set of values. So, and of course you can see if you have one number to go in, you can only come back with one number, which is the ratio. If I want to get both of these things, I need to give it two pieces of information to start. So this is always a problem when you're doing inverse problems or remote sensing, is that you have to be careful about whether or not you actually got the right answer and not one that's just a possible mathematical answer. Okay, so to solve an inverse problem, you usually either have to add constraints to the solution which will eliminate the wrong or the unphysical mathematical solutions. So maybe you know that the absorption coefficient in this problem has to be less than or equal to 0.1, and that would eliminate that solution. Or you have to add some new information of some sort. Maybe you know that the beam C value, for example, and then you can use that to pin down what's going on. And the other possibility is you solve for less information. You only solve for the ratio rather than the two values themselves, and then you can get a unique solution. So you always have to worry about non-uniqueness with any kind of inverse problem, whether it's in here or somewhere else. Here's an example from a fellow ex-student of this class who put an LU and an ED sensor on a glider, ran it around in Puget Sound, and then what he would like to do is take the LU and the ED and retrieve A and B and BB. Well, you sort of know to begin with, he's not going to be able to get all of that. But here's some plots of actual data. So here we have the backscatter coefficient, absorption, and the total scatter. And he took here's LU at 490, what particular value he measured, and ED at 490, the value that was measured there. And then what he did was he ran a numerical model, and he said what values of LU and ED, or sorry, what values of backscatter, absorption, and total scatter would give me these values for the light field, and this is at a particular depth here. So he runs the model, and he finds out, for example, to get this value of LU, I can have, you know, a high backscatter coefficient and a lower absorption, or I could have lower backscatter and higher absorption. And so I get a whole set of BB and A values that go along this line here. And for ED, I get values that would reproduce ED that kind of lie along here from low B and low A up to high BB and high A. And then the only solution where these two cross right here, and you've got the same LU and ED light fields, that then gives him the value of BB and the value of A to surprisingly good accuracy. So he's got two numbers, he's able to retrieve two numbers. Makes sense. In a 3D view, here are these surfaces, but this point here has a total scattering coefficient that's just somewhere along this line. So it's going in and out here. So from just these two light field measurements, he really can pin down very nicely backscatter and absorption, and he can't tell you anything about the total scattering coefficient. So to get that, he then also has to have a measure of beam attenuation. And then he can come in and say, well, I now know the absorption, I know the beam attenuation, and now I can get the total scattering, and that comes up and says, here's the actual point that gives me what I want. But he had to add this extra information, which was the beam attenuation. So that's just the way this whole, non-uniqueness business works. Okay, so when you think about the remote sensing problem, what you're starting out with is incomplete light measurements. So maybe you only have RRS at selected wavelengths. And you have other things you're not sure about, like the atmospheric correction, the boundary conditions, the wind speed, whatever it happens to be, water depth. And you want to feed those into some simple math model, like this, for example, and you get out some limited set of information, which might be chlorophyll or bottom depth or whatever it happens to be. And you may have a non-unique solution. So you have to come back and add some more information or constrain the solution and feed all of that in, and then you'll get an estimate of IOPs or chlorophyll or bottom depth. And this is not a solved problem. I mean, there's a lot of ways to do this. You're never quite sure that because you've put in imperfect information and you've cooked up some constraint here, maybe you're not really getting the right answer down here. You'll always have to worry about that. So different people, given the same inputs, they'll have different models here. They'll get different answers down here. So not a unique way to do things. And this, of course, if this were a solved problem, we wouldn't have this class. We would just know how to do it, and boom, it would be done. Okay. So then you'll also see inverse models or remote sensing models, for example, described as either explicit models or implicit models. So you remember the other day we derived Gerson's law, which says absorption is -1 over E0 d ED minus EU dz. That's an explicit model. It means I have a nice formula. I measure the light field, I stick the numbers in, I get the answer. An implicit model, you don't have something like this. What you do is you take a forward model like Hydrolite or Monte Carlo, and you guess some IOPs and whatever inputs there are, and you solve the model and you get an answer. Let's say for, in this case, for the irradiant or for the remote sensing reflectance, and it disagrees. Well, then you change the inputs and you run the forward model again. You get a new prediction for remote sensing reflectance, and maybe that's closer to the one you measured. And you keep cycling through this, maybe thousands of times, maybe 3 times. And eventually you'll find a set of inputs like IOPs that reproduce what you measured, say remote sensing reflectance. And then you say, okay, this must have been the IOPs that were in nature. Very commonly done thing. And if you have a rational way to change the inputs each time, hopefully this whole process will converge and you'll get a good answer. But you always have to worry about that. So explicit and implicit solutions you'll see referred to. Okay, we've already seen a good bit with these AOPs that are used for remote sensing. So we talked the other day about irradiance reflectance. That's just the upwelling plane irradiance divided by the downwelling at some given depth in the water and some wavelength. And then here we saw this figure. This is a pretty good AOP because there's a big separation with the chlorophyll value from low to medium to high, but there's still a lot of noise there. And Colin will have a lecture in a lab on semi-analytical methods. She's going to use data from, I don't know, this was like 1993 or somewhere, when she took RRS data, developed techniques to invert that to get IOPs, and you'll have a lab on that, but that's what's going on there.
Also, the data set that you generated.
Yeah, and then we also talked about the water leaving radiance, and you guys have now faced the ugliness of how do you actually get the water leaving radiance out of the total upwelling, so I won't comment on that. And then that leads to defining the remote sensing reflectance, which is the water leaving radiance in the air divided by the incident downwelling plane irradiance in the air. And you guys have seen that. And of course, people usually talk about RRS as though they're looking straight down. But really, of course, you maybe are looking off to the side. That's where this BRDF correction comes in, and on and on. And we talked about that the other day. So we then saw this figure which says RRS gives you a better AOP than the irradiance reflectance R. There's less variability due to environmental conditions, but still the same separation due to what you're interested in, which in this case would be chlorophyll. Okay, and then there's still effects of the fact that you made your measurement looking off here, and it would be nice if we could normalize that to looking straight down. And so that's what leads to this so-called exact normalized water leaving radiance and so forth that we talked about. Jeremy Wardell will talk about again next week. And then there's several ways that people estimate LW from the measured upwelling total, and you guys have now already done this, so I'll just quickly go through it. But the old kind of classical technique, which now gets called the Carter method, was by Ken Carter, where you're looking down at the ocean and you see the total coming up, which is surface reflected and water leaving, and so you make that measurement. Then you look at the angle upward, that if the surface were exactly level, a mirror surface, that would be the angle that reflects directly into your sensor. So you make that measurement, and then, here's the geometry here, and then you put in the gray card here, and we haven't seen it yet, but assuming this is what's called the Lambertian reflector, then the reflected radiance, which is what you're measuring, is equal to the downwelling irradiance times the reflectance of the card divided by pi. So you can make this radiance measurement and figure out what ED was going down. That's the ED you need to compute remote sensing reflectance. And it's funny, I don't know, those gray cards are not still here, I don't guess, but I noticed the package of the gray cards. Yeah, manually, it's kind of funny. It says, well, it had the label on it, but anyway, it says digital gray cards. Like, these are good for digital cameras, but no, this is a gray card. It just reflects light. The card doesn't know whether it's going into a digital camera, a film camera, or I'm just looking at it. And, but they were really hyping it on the big label that these were the latest digital gray cards. And I remember a few years ago there was a big buzz about you should get a digital antenna for your digital TV. No, antenna is just an antenna. The signal is either digital or analog, but the antenna is the same. But I think probably a lot of people went out and bought new antennas that were exactly the same as old ones, but they thought, well, I've now got a digital antenna. So feel free, if you've got a gray card that's 20 years old, you can still use it with your digital camera. So Ken?
Recently, we've done a bunch of BRDF measurements of the gray spectralon versus white spectralon, and you guys used a white spectralon plaque, I believe, out of the dock, and you saw how good that worked in terms of getting downwelling irradiance. The white spectralon, what we found recently is the white spectralon works really well. The gray spectralon, the BRDF, is not anywhere near Lambertian, and that method is not really recommended.
Okay, now, I was on a cruise, a Navy cruise one time, and they had this spectralon plaque, and so they've got some Navy, I don't know, low-level guy, whatever, but he had been trained how to do this, and somebody, I guess, had told him, like, don't get this spectralon plaque dirty or anything, or it'll screw up the measurements. So he's been guarding this spectralon plaque for 10 years to make sure nobody touches it or anything, and it's literally red. It's got so much scuzz growing on it that it's, I don't know, it's almost the color of the red in this shirt. But you look at this, and it was like a pinkish red spectralon plaque. And I said, dude, you know, you need to clean this. And, no, no, no. They said, don't touch it, you know, it'll ruin it. So anyway, he's been getting 10 years worth of data with a red spectralon plaque, but he had never touched it, so it was in pristine shape. But it's been, you know, sitting on a ship somewhere, molding and getting algae or whatever growing on it. So once again, you got to look at who took the data, where they took it, what instrument did they use, and decide whether you believe it. But anyway, this Carter method was a real revolution because you can do everything with one radiance meter. That's the whole point. Otherwise, you would have had to have a radiance meter calibrated and an ED meter calibrated and get those things to make sure they're in agreement. Here, if there's a multiplicative error in your radiance meter, it's going to cancel out when you plug in the numbers here. So there's this, we somewhere come down here to get the surface reflectance. As you guys have learned, you figure that what's reflected off the surface is some fraction of what you measured looking at the sky. Then you can get the water leaving radiance as the measured minus the surface reflected. The can of worms here, of course, is you don't really know what that reflectance is, because that depends on viewing direction, sun angle, the waves on the surface, and a little bit on wavelength as well. So it's still a lot of guessing, and the only time you really know this is if the water is absolutely level and the sky is nice and clear, then it's the Fresnel reflectance of the level surface at that angle. But as soon as there's waves on the water, well, you're looking in the sky at this direction, but there's a cloud over there. So the cloud's going to hit the wave tilted just right, reflect some cloud radiance into your sensor, which you're measuring looking downward, but looking upward, you're not looking at the cloud. So then this becomes uncertain, and it's basically just a guessing game. Yeah.
Would it be possible to estimate this parameter with the, like, empirical techniques?
So
with wind speed?
Yeah, so I did this paper back in '99 because people were, well, we'll see a figure in a minute. People were simply using the Fresnel reflectance of the surface, and it would be like 0.022, regardless of wind speed or anything. And I said, no, this can't be right. And so I did this big Monte Carlo study and computed these reflectances as a function of wind speed, sun angle, and viewing direction, and put out a table, which I think you guys have in the library. So you can at least say, well, I was out here, the wind speed was 5 meters a second, the sun was at 30 degrees, and if I'm looking at, you know, let's say the sun's over here, it's at 30 degrees, I'm looking at 90 degrees or 135, and I was looking at 30 or 40 degrees off nadir, then here's at least a better guess for rho than just the Fresnel reflectance. So rho might be 3%, not 2.2%. And so people have now started using that. I think pretty much everybody does, keeping in mind, of course, that it's still a pretty approximate table of numbers that's not necessarily correct. Ken?
Yeah, I'm sorry to interrupt you.
Oh, no, go ahead.
The protocol document that's going to be coming out soon, the recommended as-viewed angle is 90 degrees, not 135. And the reasoning for that is that a lot of times the way the ship's 90 degrees will put you farther away from the ship than typically the way they orient ships at 135. And the the other is a heck of a lot easier for people to figure out 90 degrees than 35. And so the protocol documents that are 90.
Yeah. Well, I won't lose any sleep over that. So the bottom line is you make these measurements, and of course notice if L is 10%, your radiometer is 10% too big, then this is too big, this is too big, and this is too big, and those errors cancel out. So anyway, that's the Carter method of estimating remote sensing reflectance. And I always say, for something like this, you estimate it because you don't really have an instrument that measures it. You're getting it from something else. Okay, I think we've said all of that. There is, I think in the library, this thing called row table, something like that. That's this table of values. It's better than nothing, but it's far from perfect. Now, what I did in that, here's just a couple of figures from the paper. In this case, we're looking at the row value versus the viewing angle for the sun at 20 degrees and a wind speed of 10 meters per second. Or sorry, here's the sun at 20, 30, 40, 60. And you can see here, if the sun is really up high in the sky and you're looking in whatever direction it was, it's easy for that light to hit a wave facet and reflect into your sensor. If the sun is lower in the sky, that light is tending to go off in this way, so you have to really have a wave facet tilted much more to take this light and reflect it into your sensor. So that's why for the high sun angles, and you're looking at a viewing direction almost straight down, you get a lot of contamination from the direct sunlight being reflected upward. When the sun angle's low and the viewing direction is large, then you really mostly just have reflected skylight, not reflected sun glint. So the row value goes down. But then if your viewing direction becomes too high, then that sunlight or skylight from over there is being reflected into your sensor, and the Fresnel reflectance really starts to go up after about 60 degrees. So that's why after 50 or 60 degrees, that reflectance factor really goes up, and it then starts to look sort of like the dotted line here, which is the Fresnel reflectance. So you do a lot of runs like this and say, well, in this case, you know, for a sun angle of 40 degrees or so, I should be looking at a viewing angle of, you know, maybe 40 degrees off nadir. Here's a different plot. This is viewing angle, reflectance, a wind speed, and then sun angle of 30 degrees. So here's a wind speed of 15 meters per second, 10, 5, 2, then 0. So if it's 0, this curve is just Fresnel reflectance. But for a 5 meter per second wind speed, you know, a viewing angle off nadir of say 30 degrees or so gives you this area where the curve varies the least. If you look right at nadir, you know, it's going up. If you look too far away, it's going up. So I just played around with this kind of stuff. Here's a plot. Here's the sun over here, and then contours of what's the correct row value, and I know the correct value because this is numerical simulations, and then viewing direction of 90, 135, 180. So there's kind of a broad area here where there isn't much variability in this row value. And then of course if you were actually looking towards the sun, then the row values become very high over here, not even contoured. So I came up with the idea that you'll probably make the best guess for row if you look at something like 135 from the sun's angle and then somewhere around 30 or 40 degrees off nadir. So that was my recommendation in the paper. Ken was just saying that the new protocols will say look at a right angle to the sun, so you're looking right up here. Well, you're still in this little region of not much variability, so I'm cool with that as well. And like he said, it's a lot easier to look at the sun there and say, ah, there's the 90 degree angle right here rather than here. And of course, you can't look over here because you're looking at your own shadow. Even though, in some sense, that would be an even better direction, except that doesn't account for the shadow. Okay.
Have you ever combined that with the sky radiance to see if rho times the sky radiance?
Well, these were computed with sky radiance distributions for a clear sky. Yeah. So, and that's probably reasonably well done in these calculations. Now, I also had in the paper some cases where I sprinkled around artificial little cumulus clouds and stuff, and then it just gets so ugly. So once again, do this on clear days, and life is much easier than on partly cloudy days. Okay.
You'll also see people or hear of people that will be trying to do this remote sensing thing. They look up at the sky and there's a cloud there, and then they'll go, "Oh, there's a cloud. I don't want to do that. I'll just go right over here where there's no cloud, and I'll measure the sky there." Does that make any sense to you all? No, don't do that. But people are doing that.
Yeah. So when you've got the worst situation is a partly cloudy sky, and there's just no way you're going to ever get it right. So you just hope for the best, and keep in mind that you got some really big error bars on your RRS value, because you're almost guaranteed that you got the wrong rho value because of looking here, even if it's a clear patch of sky, but there's these other clouds and they're all reflecting into your sensor, but you don't know how much. There's just no way to know. And then Zhongping Li came along and said, well, remember this rho thing also depends on wavelength. And I said, yeah, I know that. So anyway, he wrote a paper on that. So that just makes it all that much worse. Then there's the Li method, which you guys did. And I got to tell you, Zhongping Li is really good in that he has no qualms about questioning and redoing the way people have been doing it for the last 30 years. It doesn't matter whether it's the Carter method or it's how to do Secchi depths or whatever. He just comes on and says, I think we ought to look at all of this again and start from scratch. And maybe he gets it right, maybe he doesn't, but who cares? He's doing the questioning, and that really forces the community to think about, just because the great theoretician Preisendorfer did something in 1960 doesn't mean it's still the best way to do it. So my hat's off to Zhongping. He's really a good guy. Anyway, he came up with this idea of putting a little shade on here to block the skylight that would be reflected off the surface. And as you guys learned, if you're on the dock, that works fine. If you're on a big ship and you're 15 meters above the sea surface, not so easy to do, or if there's big waves. But in principle, it works quite nicely, and when you can apply it, it's a good way to do things. The other way people get remote sensing reflectance is making profiles of LU below the surface and then extrapolating that above the surface. So that's great because it eliminates this whole surface reflectance problem. And I think you guys did this on the dock, but you only had 1.5 meters of water to work with, so it's a little uncertain. But here's the sea surface, and if you measure, put your instrument in the water looking downward, and you get LU versus Z, so here's LU and here's depth, and you get some profile. Well, of course, in the real world, this is noisy, and maybe you have to start down here, and then basically you can get a KLU, and then use that and this little exponential function, and try to extrapolate from down here, where there wasn't too much noise, back to just below the surface. So you have then LU at depth 0, and then you can put some fudge factors for the surface reflectance, because remember, some of this light is getting reflected back downward and some of it is getting through. And then you can turn this into an LW in the air just above the surface. And you don't have to deal with the whole business of surface reflectance. The problem here, of course, is you, unless the water is like absolutely calm, you cannot measure LU right up to below the surface. So you start down here somewhere and try to extrapolate backwards. And then, well, what if your IOPs are not constant? So you've got, a layer of something like we had on the water out there the other day, where here's maybe the absorption coefficient actually looked like that. Well, then you've totally messed up this extrapolation from measurements down here. So there's just as many problems with measuring in-water measurements and extrapolating upward through the surface as there are making above surface measurements and trying to get rid of the surface reflectance. And it's kind of like, the next religious war, there's communities that will swear one way is better than the other way, and then, they're never going to come to agreement, I don't think. But then the other problem with in-water measurements is you've got this instrument in the water. So here it is, the sun's over here. Well, the instrument has its own shadow here in the water. And so at least for the first part of the path through the water, the instrument is not really looking at open sunlit water, it's looking at shady water. So it's going to get less upwelling radiance, and then finally it's going to get radiance from down here in the sun, but of course that's attenuated getting back upward. So Howard Gordon first looked at this whole so-called self-shading problem back in '92 here, and he did Monte Carlo simulations where he built in the size of an instrument, so it's some radius r. He put the sun angle here, he looked at the shadow, then he used his Monte Carlo code to compute LU as you vary the instrument radius and the sun angle and the water IOPs. And so then he condenses it all down and he says, how big is the error? So this is LU true minus LU measured divided by LU true. So that's a measurement of the error. And this product is absorption times the radius of the instrument. That's what turned out to be really important. So if you have a really small instrument, you're down here, the error is negligible. If you have really clear water, you're down here, so low absorption, the error is negligible. But as the product AR increases, so here's 0.01, 0.11, then this error gets to be really big, so 25% up to 100%. So if the product of the absorption coefficient at your wavelength and the instrument radius is 1, you're getting 100% error, factor of 2. If, let's say, you had an instrument where the radius was, let's say, 10 centimeters, and the absorption coefficient, so that's 0.1 meters, and the absorption coefficient was 0.1 per meter, and then so that's 0.01, then you're down right here, 0.01, you'd be having like a 5 or 10% error. If you have an instrument that's, let's say, a big one, or just say the absorption coefficient was 0.5, now we're looking, and maybe this is 20 centimeters, so 2 times 5 is 10, so that's a 0.1 if I did the arithmetic right. And so now we're out here, and now we're looking at, 30% error. So it's not a negligible error, and you have to then, do some correction for your measurement, your sun angle, your water IOPs, or you're going to be in error by possibly tens of percent. So this is a real incentive for people to make instruments as small as possible so they have as small a shadow effect as they can get. Okay, so that just kind of summarizes what I said. Yeah.
How did Gordon and Ding measure true upwelling radiance?
Well, they were doing Monte Carlo simulations, so they knew the correct answer from Monte Carlo. You run it without the instrument, then you do the simulation over with the instrument and look at the difference. In the real world, you know, then you don't know the true because you always have the instrument there. Okay, so enough said there, I think. And I just said here the in-water measurements have just as much uncertainty as above-water methods. And there's this Mobley's law of conservation of misery, which says, you know, I don't care how you do it, you got problems. And so there's a number of unrecognized laws that I've developed that should be in the physics books, but they're not. The other one is Mobley's zeroth law of optics, which says if the light doesn't go in your eye, you don't see it. And so, you know, you see the Star Wars things with the lasers going through space, and they always are red and they make little pinging sounds. But if there's nothing in space to scatter the light out of the laser beam, it won't go in your eye and you won't see it. But Hollywood's not aware of that. So anyway, there was a big comparison of methods by Hooker and Company a few years ago. This is just a diagram of all these different ways they tried to cook up or ways they used to estimate remote sensing reflectances. So they had, you know, both above water and in water measurements. They used moorings, they used profiles, they used floats, etc. And then here's a plot. Here's one of their in-water methods versus the above-water methods. And if you're really, really careful and you do everything right, and you can get pretty good agreement between them. And then let's see, now that was it. Anyway, you know, they will both give you the same answer, but they both have kind of problems of equal magnitude that you just have to really worry about the details. Okay, so then to finish up here, there's this atmospheric correction problem, which is the tough part of remote sensing. So if you just think about, here's the sun, here's our satellite looking downward, measuring radiance at the top of the atmosphere. So what all does it really measure? Well, there's radiance that comes in from the sun. It gets scattered by atmospheric gases, so that's so-called the Rayleigh contribution or the Rayleigh scattering part. So and it could be single scattering, it could be multiple scattering, so that you're measuring. Then there's specular reflectance from the sea surface, shown in yellow. So that's going to hit the surface and bounce off. And you do your best to avoid that by simply not looking in the direction that will give you a lot of specular reflection. But there will always be the occasional wave facet that's tilted just right to give you at least a little bit of specular reflection. And then, so there's aerosol particles I stuck in down here. So you get light that comes in, it scatters off an aerosol and back up to your sensor. You can have the so-called Rayleigh aerosol interactions where light scattered off an aerosol and then off of an atmospheric molecule, or vice versa, it scatters up here and then off of an aerosol. So that's treated separately by NASA. You can get reflectance off of clouds. You can get reflectance off of white caps on the surface. And then finally, what you're actually interested in is there's water leaving radiance coming out that makes it up to your satellite. So the atmospheric correction business is to take all of these contributions in some way, account for them, and just end up with the water leaving radiance. Then you can kind of figure that's going to be a hard problem just by looking at the cartoon. Okay, so I have, for some examples here coming down the road, there's a code called ModTran, which is kind of the atmospheric version of hydrolite. So ModTran works in the atmosphere, hydrolite works in the water. And it's a long story, but I coupled those two guys together and that was then used in the design of the Veers instrument, 10 years ago or so when they were building that. But it was a weird deal. I tried to get the Navy to fund me to couple Montran and Hydrolite together, and we'd have a coupled atmosphere